Okay, so what does first function look like? What is first function? What's it called? Linear. What's characteristic? Straight line.
You have to use the boxes.
What?
What are you talking about?
What?
Okay.
You have to use these equations into
Write the equation, each of the following functions in the same box.
Just write the letters.
Yeah.
Oh, gotcha. You mean in here?
Yeah.
Yeah, but they have letters, right? Okay. Well, I don't know. Well, so let's make this smaller then, right? How do I make it? Oh, there we go. There, how's that? Now we'll have room. Okay, what's this guy? What's it look like? Okay, so name? Quadratic. Characteristic? Parabola. Parabola. Ebola. So it's a U-shaped curve, right? U-shaped. Next one, what kind of shape's this guy? It's a cubic. Shape?
Two curves.
Two curves, not really.
Is it one way up?
Still not two curves.
What is it going on? Or one curve?
It's one curve.
One infinite curve. And it has three, it has three intersections into the x-axis.
No, that would be the
so it's kind of I don't know, S shape.
I always thought of it as
It's the year of the cubic, right?
snakes are linear. It's a year of the cubic.
Okay, so snakes could be linear, quadratic, or cubic, I guess.
Or
Or they could be the next one. Two snakes we'd need for the middle one at the bottom. And yeah, one snake might do if it could bend into a V shape, or two snakes.
They'll probably bite you first. Yeah.
Depends what kind of snake it is.
Python?
Okay, what's next? What's the next one?
It's called the graphs like
He's beautiful.
C-shape.
This guy.
C-shape.
C-shaped, half a parabola. So, what's the name?
Logarithmic. Oh, wait, no. Quart. Oh, it's square.
Rootic.
Rootic.
Be a rootic.
Let's call it a square root.
No, it should be a rootic.
Or, if you want, we can be radical. Although you should always strive to be rational, but especially when radicals are involved. Next one. This is rational. What's it look like? Yeah. Would take two snakes. Or you have to lift your pen if you're drawing this, right?
Maybe an infinitely long snake that curves.
Yes. Characteristic, two pieces, asymptotes. Next one.
Absolute value.
Absolutely.
Stop considering dad puns. Puns.
Sometimes I do value your opinion.
No, you don't.
Absolutely not. Characteristic. V-shaped.
Why are you doing that?
Go back.
What?
Why are you doing
No snakes were harmed in the making of this. Wait a minute, have I showed you any Vi Hart videos?
No, only one, but that was pretty different.
Shitting me.
Oh, okay. I think she's got one with snakes. What's the next one? Exponential. I'm glad you came up with the name because I couldn't think of it at the moment. What's that? Exponential. What's it look like? Oh, it looks like this. Yeah.
See, I was right.
Characteristic?
It's a cat.
It's got an asymptote.
Yeah. It looks like a big cat.
Now, Vi Hart draws slug cats.
Yes. Now make it a cat.
Never touches the axis.
Yeah.
Gets as close as you want, but never quite gets there. Has that shape. It has that shape. It looks like that. Write the equation of each of the following functions, or put the letter for each one, I suppose, right? In the same box as the basic function that shares similar characteristics. Hint, there will be a total of 4 functions in each group. For each group of functions, describe the common characteristics. I already did that. We'll name the functions together later. Oh, or sooner. Because we already named them. I guess you were supposed to do this first. Oh well. I'll pause. So we'll scroll this up and leave it visible for a moment. You know, so if you're looking back, or if Dan doesn't show up and has to watch this, he can see these answers.
I don't think you watched it.
No, this is unpaused. I don't think anyone does either.
I heard somebody watch it. I heard my voice. So yes. I don't think anyone will watch this.
Okay.
Unless I got something like yes.
Next page. For each of the following equations of basic functions, complete the table of values. These points will be your key points. Use the key points to sketch the graph. Also state the domain range, x-intercept, and y-intercept. Okay, do it.
Unpaused.
On to quadratic. Okay, so all graphs are drawn to the extent of the grid, right? Nothing from nothing. Can I go where?
Hall. Did you say that? Dude, it's so easy. It's all above zero than X belongs.
Okay. There's the rationals. How we doing? You got your rational, you got your whatever was above rational, radicals.
We see the radicals.
We stay real, right? Keep it real.
No.
They can't keep it real if it's not real.
Why is it not real?
Keep it real.
I don't have a wow. Actually,
Well, how are we going to graph it otherwise? We don't have a complex planes anymore.
exactly.
That's the good thing.
That's what I told you. Holy.
Yes, it's 2I, but no, we don't write that.
I put a file.
Yes.
Max negative. That over. What's his definition?
Are you talking the number?
Yeah.
Oh,
Is it still
wow.
recording?
They're talking World of Warcraft.
No. The actual definition.
Legal
of
legend
wow.
that
See, I got it right. Number wow.
It is everything and nothing.
It's everything. Shut up.
Okay. Radical, there's rational. Let's do exponential.
2 to the negative 3.
1/8.
What?
1/8.
You're really bad at this.
Oh.
You're really bad at this.
What have you learned from radicals?
Nothing.
Has Miss McCain not taught you everything?
I wasn't in Miss K.
Who
Why
were
are
you?
you here then? Go away.
Read divide by 0.
Why don't you
Okay, yes, sir.
Will open up in the ground.
Right there. Your epsilon for
Why is it going off at the end? That's a
Where would you have it go?
exponential function.
Okay, in this investigation, keyword investigation, you, next keyword, you, will examine the effects the degree and the sign of the leading coefficient have on the graph of a polynomial function. The equations of polynomial functions below are expressed in both simplified form and factored form. Use a graphing technology. So, my favorite is Desmos.com. Have I shown you that before?
No.
Oh, okay. Let me show you
Yes.
that.
No.
A lot. Traders.
Go to, open up. Oh, here we go. Desmos graphing. Doing his writing on it. Put the pen
I think there's an error. Your line's red.
Okay, so this is desmos.com, desmos.com. When you go there, just say launch calculator, and you can put in expressions. And what I like about it is, you know, if you start off with y equals x, then there's y equals x. But if you then decide, oh, I want to make that squared, so you go with a shift 6 to kick yourself up there, then you get x squared. Right? And then if you do something like go minus 3, then immediately it becomes y equals x squared minus 3, right? And then if you change that to minus 3x, then you immediately get x squared minus 3x, right? And then you go like plus 4, and you go equals 4, then it says, what the heck are you talking about? So you go plus 4, and there's y equals. So we start off with y equals x, the straight line, into x squared, then minus 3, then over there, because it was minus 3x and up 4. So you can see at each stage what you're graphing. So that's nice to graph on. It gives you a nice grid. You can run it off your tablet. You can run it off your computer. I think it's HTML5, so you don't have to worry about having Flash or anything like that. You can run it, might be able to run it off your phone as well, but it'll be kind of smallish on there. Or you can use your graphing calculator, keeping in mind that you will have the graphing calculator available most of the time to you when you're doing math, right? Except for like one of the IB exams, and then occasionally we might run the odd quiz where we don't want you to have the graphing calculator. Okay? But there is one there is one of your IB exams where there are no calculators, right? So
Yeah, is that this year or
next year.
What is it on?
It's on everything you did in the 4 courses that precede it.
Oh, crap.
No.
Okay, so anyways, in this investigation, you will use some graphing technology if need be to graph these to find the x-intercepts. Remember, x and y-intercepts are numbers. They're not points, right? It's not the point that the line crosses the x-axis. It's the value of x when the curve crosses the axis. It's the value of y when the curve crosses the y-axis. Okay, so these are numbers, not points. If there are multiple numbers, separate them with a comma. Do not, if there are two x-intercepts, put a comma between them and then throw brackets around them, because that will become a single point, which will lose you a single point on whatever marks that was worth. Okay, so numbers only. Relative minimum points are in fact points, must be enclosed in a set of parentheses. Relative maximum points, again, domain and range, you can kind of abbreviate, okay? So if we're going to say that x is greater than or equal to 0, you don't need to also put that x belongs to the reals. We'll assume that. And you don't need to write the whole necessary set notation, because there's not a lot of room in here, right? So you can just abbreviate it as x is greater than or equal to 0, or y belongs to the reals. Good enough. And the graph, sketch out the graph, okay? So you want to do that for all of these. And then it moves down somehow. And then you want to start to examine the connection between the degree of the polynomial and the shape of the graph, and the connection between the sign of the leading coefficient and the end behavior of the graph, and use your findings above to predict the following polynomials. So degree 6 and degree 7. Okay. Then it moves on. Write a conjecture about relationship between degree and the shape, and a conjecture about the relationship between the sign of leading coefficient and which quadrant the graph appears to end. And continue on, here's a polynomial function, and then determine the y-intercept of each of the following, and then blah, 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 right? And use your newfound knowledge and what you already know about the effective degrees to not use graphing technology to sketch out a possible graph. Okay, what would this graph look like? So it doesn't need to be exact, but certain characteristics need to be there. All right, there you go. So, okay, so when we're talking about minimums and maximum, right? I mean, this has no minimum and no maximum, right? It goes on forever in both directions. What do we call this point here? Minimum. Now, it's actually the absolute minimum, right? In other words, it never gets lower than that. Okay, so that would be called an absolute minimum. Who cares? Okay, then you get a cubic. Now cubics can do this. So in a cubic, this is called what? A relative maximum. It's not the maximum because there isn't one, right? And it goes up to infinity. So this is a relative. So relative to all the points that are around it, this is the maximum. And this one here is a relative minimum. Okay? So cubics do not have absolute maximum or absolute minimum, right? But they may have relative. They may not, right? The one that we first drew has no min or max, right? It just has, so those relative min or max, another word for them would be a turning point. Okay, that's where the graph is turning. And then there's also other points on the graph. So on a cubic that looks like this, there are no turning points, there are no relative min or max. This is called a point of inflection.
Why did you lie? You said that previous graph was a cubic. And I told you it wasn't.
How is this not a cubic?
It's not cubic.
What is it?
It is a cubic.
Is it quadratic?
No, it's a sine curve.
Is it quartic? Oh, it's a sine curve. Because sine curves go up forever.
Yep.
Unlike your mark, which apparently is not a sine curve. This is a sine curve.
No, it's a sine curve.
Okay, you say it's a sine curve.
That's